Infinities can act pretty funky. If you're interested in why that is, please see my playlist on YouTube on the philosophy of infinity. We might then worry that a language built out of an alphabet with an infinite number of symbols would not make sense. And there might be concern that our language of PL does just that. But as we'll see here, that actually doesn't have to be the case. First, let's see why this might be a problem. We said that capital letters A through Z are all basic propositions. Now there are 26 letters there, so that we have 26 basic propositions. Of course, we may need more than that. So we adopted the convention of subscripting these letters. A, then A sub 2, A sub 3, A sub 4, B, then B sub 2, B sub 3, all the way through Z, Z sub 2, Z sub 3. And don't forget, we chose not to write A sub 1, B sub 1 because we typically won't be subscripting these things. We typically won't need more than 26. And it might be confusing to have an A and then have an A sub 1. You might wonder, isn't this A the A sub 1? In any case, let's just first consider just the A's. A sub 2, A sub 3, A sub 4, all the way so forth. We have A, which is a symbol, we have 2, which is a symbol, we have 3, which is a symbol, 4, which is a symbol. So we have these numbers as symbols as well as the letters, but there are an infinite amount of numbers. If each number is a symbol, then we're left with an infinite number of symbols. The English alphabet has 26 letters, so the alphabet of PL will have those 26 symbols plus an infinity of symbols with the numbers, minus of course the number 1, which is still going to be an infinity. How do we deal with this problem? Well, the idea will be not to count each number as a symbol. Instead, we're only going to count the digits as symbols. So for example, 0 through 9 are all digits. There are 10 digits there, so that would be 10 symbols. But the number 10 is actually made of 2 digits, 1 and 0. So that would be actually 2 different symbols. 10 wouldn't be a new symbol. And the same thing with 11. Well, actually 11 would be 2 tokens of one type of symbol, the digit 1. And if you've forgotten all about that token type distinction, you can check out our earlier video on that in chapter 1. In any case, you would just go on from there. So 12 wouldn't be a new symbol. 1 and 2 are the digits, so those would be symbols. 12 would be made up of those two symbols. And notice, what we've done here is that we've made sure that the number of symbols are finite, but we've left open the possibility of an infinite number of actions that could create an infinite string of symbols. We haven't said that that's actually the case, we've just left it open. So let's check out this possibility in a little bit more technical way. First thing we're going to do is to define what a basic proposition is using this new idea that we've got here. Number 1 is going to start off that any capital letter A through Z will be a basic proposition. Number 2, we're going to say that any of those capital letters throw some kind of finite string of digits as a subscript, and that is also a basic proposition. So if alpha is a capital letter, A, B, C, D, all the way through Z, and X is a finite string of any of the digits 0 through 9 that doesn't begin with 0, then alpha sub X is a basic proposition. And of course we have that proviso, except where X is the string 1. And remember, that's because we said that we weren't going to count A sub 1. We're just going to use A, not A sub 1. Finally, 3, nothing else is a basic proposition. Did we cheat here? What exactly do we mean by finite string of digits? Let's define that too. A finite string of the digits 0 through 9 that doesn't begin with a 0, or we'll call it FSD for short, finite string of the digits. Number 1, each of the single digits 1 through 9 is a FSD. 2, if X is an FSD and Y is one of the digits 0 through 9, then take X, add Y onto the end of X, and you also have an FSD. Number 3, nothing else is an FSD. What kind of a definition is this, by the way? Recursive definition. And if you don't remember what a recursive definition is, then you can go back and watch the video on recursive definitions. Why is it important that it's a recursive definition? Because a recursive definition allows itself to be used an unlimited amount of times, constantly generating new stuff. But it doesn't begin with an infinity. Are there an actual infinite number of propositions? Well, with a recursive definition, we can say, not sure. But there's no limit to the amount of times that you can use this definition to generate new propositions. And hey, if you want to, man, go ahead and call that an infinity. So brief recap, the issue is that it seems like we have an infinite number of symbols, since it seems like we're taking the set of natural numbers as symbols for our alphabet. And of course, the natural number set is an infinite set. We solve this by taking the digits as our symbols and giving a recursive definition that can be applied an unlimited amount of times, and using that, hey, if you want to say that you can do it, then yeah, sure, you can get to the natural number set. In Aristotelian verbiage, that would be a potential and not an actual infinity. And this is one reason why recursive definitions are so useful. Anyway, that's the end of chapter 2. For next time, please read chapter 3, the very beginning part, those 2 paragraphs at the very beginning. And if you're interested in some interesting points, then read note 1, and I'll talk a little bit about that. And if you'd like to, you can skip that part and then go to the next video. So the video after next, we're going to be doing 3.1 truth tables for connectives. You can get started with that one if you want to.